Greetings everyone. This is Dr. A. Maheswari from Mathematics Department, Kamaraj College of Engineering and Technology, Virudhunagar. In this video, we will discuss about Poisson distribution. First, let's see the definition of Poisson distribution. A random variable capital X is said to follow Poisson distribution if it assumes only non-negative values and its probability mass function is given by P of capital X equal to small x. This is equal to e power minus lambda into lambda power x divided by x factorial, where x equal to 0, 1 to infinity and lambda greater than 0 is known as the parameter of the distribution. And capital X is a Poisson distribution. It is denoted as P of lambda. Lambda is the only parameter of the Poisson distribution. Next, moving on to the applications. Number 1, the number of customers entering a post office or restaurant on a given day. Number 2, the number of accidents in some unit of time. Number 3, number of typing errors on a page of a book. Number 4th one, number of network failures per day. Next, we have to see the conditions for Poisson distribution. Poisson distribution as limiting case of binomial distribution under the following assumption. Number 1, the number of trials n should be indefinitely large, that is n tends to infinity. Number 2, the probability of success p for each trial is very small, that is p tends to 0. Number 3rd one, lambda equal to np is finite. Then 3 condition. Number 1, n tends to infinity. Number 2, p tends to 0. Number 3rd one, lambda equal to np is finite. Next, we recall some formulas in differentiation and exponential. Number 1, differentiation of x power n equal to n into x power n minus 1. Number 2, differentiation of constant term equal to 0. Next, differentiation of e power ax equal to a into e power ax. Differentiation of uv equal to u dv plus v du. E power x equal to 1 plus x by 1 factorial plus x square by 2 factorial plus etc. E power 0 equal to 1. E power x into e power y, this equal to e power x plus y. Next, definition of moment generating function. The moment generating function of a random variable capital X is given by mx of t equal to capital E of e power tx. Capital E denotes expectation. This equal to summation e power tx into p of x if capital X is discrete, where the summation is taken over the entire range of x and t being a real parameter. Next, properties of moment generating function. Number 1, m cx of t equal to mx of ct, where c is a constant. Number 2, m x1 plus x2 plus etc xn of t, this equal to m x1 of t into m x2 of t etc m xn of t if x1, x2 etc xn are independent random variable. The sum of x1 plus x2 plus etc xn moment generating function is equal to product of the moment generating function. Using MGF, we can find mean and variance. E of x equal to mx dash of t at t equal to 0. E of x is nothing but mean. E of x square equal to mx double dash of t at t equal to 0. E of x is also called mu1 dash. Mu1 dash is the first order moment and mu2 dash is called the second order moment about the origin. Mean equal to E of x, variance equal to E of x square minus E of x the whole square. This is second order moment minus first order moment the whole square, and standard deviation equal to root of variance of x. To find moment generating function of Poisson distribution, we know that mx of t equal to capital E of e power tx. Capital E denotes expectation. This equal to summation x equal to 0 to infinity e power tx into p of x. Capital X is a Poisson distribution. So, p of capital X equal to small x, this is equal to e power minus lambda, lambda power x divided by x factorial. This is equal to summation x equal to 0 to infinity e power tx, e power minus lambda, lambda power x divided by x factorial. E power minus lambda is constant. So, this is equal to e power minus lambda, summation x equal to 0 to infinity lambda into e power t. We go to joining this term lambda and e power t, the whole power x divided by x factorial. Next, substituting x equal to 0, 1 to infinity. If x equal to 0, we get the answer lambda e power t, the whole power 0 is 1. 1 divided by 0 factorial is 1. Next, put x equal to 1 lambda into e power t, the whole power 1 divided by 1 factorial plus etc. This is the series of exponential. So, we get e power minus lambda into e power lambda into e power t. This is equal to e power, we have to adding the power values, we get the answer e power minus lambda plus lambda into e power t. In this term, we can find the common value is lambda. So, e power lambda into e power t minus 1. Therefore, moment generating function of Poisson distribution mx of t equal to e power lambda into e power t minus 1. Next, we have to calculate mean and variance. In mx of t equal to e power lambda into e power t minus 1. First, differentiation with respect to t, we get mx dash of t equal to e power lambda into e power t minus 1. Differentiation of e power ax equal to a into e power ax. So, we go to differentiating in the power term, we get the values lambda into e power t. Differentiation of constant term is 0. Next, differentiation again with respect to t, mx double dash of t equal to e power lambda into e power t minus 1. Again, differentiation in the power values, we get lambda into e power t and lambda e power t plus e power lambda into e power t minus 1 into lambda e power t. We are using the product rule, differentiation of uv, this is equal to v du plus u into dv. This is u, this is v. Next, put t equal to 0 in mx dash of t. Mx dash of 0 equal to e power lambda into e power 0 minus 1. E power 0 equal to 1. 1 minus 1 is 0. We get the answer e power 0. Lambda into e power 0. We get the values lambda. Therefore, e of x equal to lambda. This is the first order moment. First order moment equal to lambda or mean equal to lambda. Next, second order moment. Mx double dash of 0 equal to lambda square plus lambda. Then e of x square equal to lambda square plus lambda. We have to calculate variance. Variance equal to e of x square minus e of x the whole square. This equal to lambda square plus lambda minus lambda square. We have to cancel lambda square and lambda square. We get the values lambda. Therefore, mean equal to variance equal to lambda. In only Poisson distribution, mean equal to variance equal to lambda. Next, properties of Poisson distribution. Additive property. Number 1. The sum of independent Poisson variate is a Poisson variate, that is x1, x2, etc. xn are independent Poisson variate with the parameter lambda 1, lambda 2, etc. lambda n respectively. Then x1 plus x2 plus etc. xn is also a Poisson variate with the parameter lambda 1 plus lambda 2 plus etc. lambda n. Given x1, x2, etc. xn are Poisson variate. So, mx of t equal to e power lambda into e power t minus 1. In general, mx I of t equal to e power lambda I into e power t minus 1. Using the property of MGF, m x1 plus x2 plus etc. xn of t equal to m x1 of t into m x2 of t etc. m x1 of t. Substituting the values of m x1 t and m x2 t and m xn of t, we get e power lambda 1 into e power t minus 1. Next one e power lambda 2 into e power t minus 1, etc. E power lambda n into e power t minus 1. Adding the power values, we get e power lambda 1 into e power t minus 1 plus lambda 2 into e power t minus 1 plus etc. lambda n into e power t minus 1. In this term, the common value is e power t minus 1. We have take out, then e power lambda 1 plus lambda 2 plus etc. plus lambda n into e power t minus 1 is the MGF of Poisson distribution with parameter lambda 1 plus lambda 2 plus etc. lambda n. By uniqueness theorem of MGF, x1 plus x2 plus etc. xn is also a Poisson variate with the parameter lambda 1 plus lambda 2 plus etc. lambda n. Therefore, sum of n independent Poisson variate is also a Poisson variate. Property number 2. The difference of two independent Poisson variate is not a Poisson variate. Given two independent Poisson variate, then x1 and x2 are independent Poisson variate with parameter lambda 1 and lambda 2. Since mx of t equal to e power lambda into e power t minus 1, in x1 of t, mx1 of t equal to e power lambda 1 into e power t minus 1, m x2 of t equal to e power lambda 2 into e power t minus 1. Consider m x1 minus x2 of t, this is equal to m x1 plus minus x2 of t. Next, using the properties, m x1 plus x2 of t equal to m x1 of t into m x2 of t. We get m x1 of t into m minus x2 of t. Again, using the property of MGF, m x1 of t into m x2 of minus t. Since m cx of t equal to mx of ct, here c is minus 1. So, we get mx2 of minus t. mx1 of t is e power lambda 1 into e power t minus 1. So, e power lambda 1 into e power t minus 1. Next one, e power lambda 2, this is minus t. So, e power minus t minus 1. This cannot be written in the form e power lambda 1 minus lambda 2 into e power t minus 1. Hence, x1 minus x2 is not a Poisson variate. Therefore, difference of two independent Poisson variate is not a Poisson variate. Thank you.